Okay, so let's start. Uh, can we maybe turn off some of the fans? Can we maybe turn off some of the fans or it's fine. Okay, so in the last class we were talking about Reed-Muller codes. We concluded our discussion on Reed-Solomon codes and then moved to a new class of algebraic error correcting. So recall that one way of looking at the Reed-Solomon codes was basically you take a polynomial, the message polynomial, and you evaluate it at all points at a certain set of points, alpha 1, alpha 2, up to alpha n. So you choose n different points in the finite field, and the Reed-Solomon code word is obtained by evaluating the message polynomial at those n different points. Right? But this requires the field size to be at least n, which in many cases is not practical. So the question is, can we construct good codes, algebraic error correcting codes over smaller field sizes? Particularly, if, so let's say I want to construct it over the binary field, right? So one way to do so is to generalize the Reed-Solomon codes, right? So Reed-Solomon codes obtained by evaluating a polynomial in one variable. Instead, you look at polynomials over multiple variables, and that is what you get is called the Reed-Muller codes. Right? So suppose you take a polynomial in m different variables, right? x1, x2 up to xm, and now the code word is essentially obtained by evaluating an m-variate polynomial, at all possible points. Right? So each point now is an m tuple. Right? So all of the m variables can take different values. So the total number of values that you're going to evaluate it on is q to the power m, where q is the field size. Right? So each xi can take q different values. So the total number of points that you're evaluating the polynomial is q to the power m. And okay, so sorry, which fp? Okay, fp, fine. It's either fp or again depending on what I'm calling the field size, right? So we're evaluating it over fq. So q is going to be the size of our field. All right. So recall that given any polynomial, we distinguish between the total degree of the polynomial versus the individual degree corresponding to each variable. Right? So the degree of this polynomial is the total degree, which is 4 plus 1, 5, or 3 plus 2, 5. So degree of f equal to 5. But then you can also talk about the degree with respect to one of the variables. So the degree with respect to x1 f is basically equal to 3. The degree with respect to x2 of the polynomial f is equal to 4. Just some notation. And can you tell me if this strictly generalizes Reed-Solomon codes? So how do you obtain Reed-Solomon codes from the class of Reed-Muller codes? Can you speak a bit louder? Okay, I mean, another way of putting it is the Reed-Muller. So if I call Rm of Q mr, so Rm of Q mr is the Reed-Muller code over field size Q. M is the total number of variables, and R is the maximum degree, the total degree, right? So for what parameters will I get a Reed Solomon code, a normalized Reed Solomon code to be more precise. Speak a bit louder. Okay, but for any M, any R, how many variables are there in a Reed Solomon code? How many variables are there? Those are the evaluation points, right? No, those are the evaluation points, alpha 1, alpha 2, up to alpha n. But it's a polynomial, but basically the message polynomial is a polynomial in how many variables? Are you sure it's n variables? Are you sure it's k variables? We're not talking about the degree, right? We're talking about the number of variables. Is it a univariate polynomial, a bivariate polynomial, or a multivariate polynomial? Correct. There's only one variable, right? X. So m is equal to 1. So m equal to 1 gives you the class of at least one specific case of a Reed-Solomon code, right? But then typically when we say Reed-Muller codes, we evaluate it at all possible points. We're not evaluating on a subset of the points. Right? So the size of the Reed-Muller code, or the block length in the case of a Reed-Muller code, what we typically take is q to the power n. Okay? So the way I have defined it over here, the Reed-Muller code is obtained by evaluating at all possible q to the power m points. So you cannot construct a Reed-Muller code for arbitrary block lengths. Right? It has to be q to the power m, or effectively the power of, it has to be an integer power of some prime. Correct? So the question is, now this is the block length. What is the minimum distance, and what is the dimension of a general Reed-Muller code? Okay. In general, it turns out that we can't get a simple closed form expression for the dimension and the minimum distance. But in case of the dimension, we can get upper and lower bounds, and we'll derive that in two different steps. So sort of two different cases. So the first case is when the field size is reasonably large, not too large, but it has to be a little bit large. So if R, the maximum degree, is strictly less than Q, then the dimension of the Reed-Muller code turns out to be R plus M choose R. Okay. So let's, is the statement clear? Okay. All right. So now what does a message polynomial look like? Suppose I take m equal to, let us say, 2, r equal to 3, or maybe r equal to 2. Can you give me an example of one example of a message polynomial? Okay, x1, x2. So it's any polynomial in two variables and having degree at most 2. Correct? So x1, x2 is one case, maybe plus 3 x1 square plus 4x2 square. This is one example. Correct? Okay. So now, if you look at this, any polynomial can be written as a sum of monomials. Correct? Uh, and in general, you can write any message polynomial in the following form. So maybe let me call it capital M. So this is the message polynomial. This is, say, again, for this particular example, I can write this as a00 x power x1 power 0 x2 power 0 plus a01 x1 power 0 x2 power 1 plus a10 x1 power 1 x2 power 0 plus a20 x1 square x2 power 0 plus a02 x1 power 0 x2 square plus a11 x1 power 1 x2 power 1. Correct? So any general polynomial having two variables and total degree at most 2 can be written in this particular form. Do you agree? I can write any polynomial in this particular form. So now, how do you choose a particular message? A message is obtained by choosing one set of these coefficients. Correct? Do you agree? Any questions? So if I put, say, one particular realization, say a00 equal to 0, a01 equal to 1, a10 equal to 0, a20 equal to 0, a02 equal to 0, and a11 equal to 1. That gives me one particular polynomial, and that corresponds to one particular message, right? And the code word is obtained by evaluating this message, which is this particular polynomial, at all possible points. Correct? For example, if I take m of x, so one particular message, if I look at the a vector, suppose I take 1, 0, 0, suppose I'm evaluating this over, let us say, f3. Okay? So this is the coefficient, so m of x. So this is one particular message, and this basically corresponds to the polynomial 1 plus 2x1 x2, right? Okay, so now how do you get the code word? You get the code word by evaluating this at all possible points. And how many points are there? Which is what? 9 points, right? So basically starting from 0, 0 all the way up to 2, 2. So if you evaluate it 0, 0, you get 1. If you evaluate it at 0, 1, you get 0, 0, 2, say 1, 0, get 0. All of these are 1. Zero, 0, 0 1 0 2 1 0 1 1 1 2 2 0 2 1. Right? So if I evaluate it at 0 2, I get 1. If I evaluate it at 1 0, I get 1. Evaluated at 1 1, I get 1 plus 2 into 1 into 1, which is 3, which is 0. I evaluated at 1 2, I get 1 plus 2 into 1 into 2, so that's 4 plus 1 5. Modulo 3 is 2. Similarly, I evaluated at 2 0, I get 1. Evaluate it at 2 1, I get 1 plus 4, which is 5, again 2. Evaluate at 2 2, 2 into 2 into 2, 8 plus 1, right? 2 into 2 into 2, 8 plus 1, 9 is 0. So this would be the code word. Okay. Now what I'm interested in is the dimension. Correct? In this case, for this particular example, what would be the dimension of this code? In this case, what would be the dimension? So in this case, what is the message for RM of 3 to 2? What is the message or length of the message vector? 6, right? There are 6 free variables corresponding to the 6 coefficients of this polynomial. So the dimension is equal to 6, because the total number of messages is the total number of message polynomials, which is q to the power 6, or 3 to the power 6. Right? Every assignment of the coefficients gives me one particular message vector or one particular message polynomial. So the dimension in this case is equal to 6. So now, if you think about this, can you generalize? In general, for any read Muller code, what would the dimension be equal to? You don't have to give an expression, but can you verbally describe what it will be equal to? How would you find it? Solutions of what? Okay. Okay. So, but there are also 0 degree and 1 degree. Correct. Correct. So basically, you look at the number of monomials whose total degree is less than or equal to r. Okay? That is exactly equal to the dimension. Correct? You all agree? So in general, the dimension of the read Muller code Q M R. This is equal to, again we're assuming that R is strictly less than Q. So this is equal to the number of monomials in m variables and having total degree less than or equal to R. Do you agree? So this is equal to, again, so every monomial essentially corresponds to an assignment of the degrees for each variable, right? So you look at all possible d1, d2 up to dm, which of course have to be integers such that each di is between 0 and r, and these di's should be less than or equal to r. So the size of this set gives you the dimension, correct? So this is a counting problem. And what does this equal? How do you find the number of integer solutions to this? So for r equal to 2, we just found out, right? For r equal to m equal to 2, right? We found that it's equal to 6. Can we generalize? Yep. What do you do? Yeah, it's just plain combinatorics, it's nothing else. So this is kind of closely related to what is called a stars and bars problem. Okay, so I have R stars and I have to place m bars anywhere in between the stars. Okay. So for example, I can place one over here, I can place one over here. I can also place multiple bars within two stars. Okay, so you think of it in the following way. There are R stars. You can place it on either. You can place a bar on either side of any particular star. So in how many places can I place this? Yeah, r plus 1 places. Okay, and how many bars do I have? M. Okay, so now is this connected to the problem that we had? What did we want? We wanted the number of integer solutions p1 to pm. Each one is an integer. Each di should be less than or equal to 0, less than or equal to r, and the summation I equal to 1 to m pi should be less than or equal to r. Firstly, are these two problems equivalent? Number of stars is fixed. You have at most okay. Bar 1 is there and bar 2 is there. You have 1 star and bar 1 to bar 1. Okay. So you have 2 bars. Yes. Here, attached to the bar. Star is in. Okay. Can give value 1. Bar 1. Which one? This one gets. Okay. Okay. Then if you consider bar 3, star is there. So if you add all these things, then we'll get the fixed number. R star. Add all those numbers. Okay. So here in this case. So what do I assign to this bar? Putting that bar and the oh, this bar and the next bar. Suppose this is the last bar. All the remaining stuff. Okay, so let's. So in this case, you would assign 2 to this. Okay, and why does this? So how does this correspond to this solution? It won't correspond. So I want an equivalence between this problem and this problem. Some. Oh, correct. Yes. Yeah, I agree. This particular mapping does not correspond to this problem. Fine. But the question is, does there exist a mapping between this and this? So for every solution here, I should find an equivalent solution here. Similarly, for every solution here, there should be an equivalent solution here. Okay. So suppose I have some solution over here. Okay, look at any pair in any m tuple of integers satisfying this particular constraint. Okay, now what do I have? I have a total of r stars. All right, so let me look at d1. So d1 is some integer between 0 and r. Okay, after the first d1 r's, I place a bar. Okay, maybe let's say d1 equal to 2, d2 equal to 1, d3 equal to 0, d4 equal to 1. This is one set. So I first place a bar after 2 stars. Then I place another bar after d2 stars. So after 1 star, I place another bar. Okay. And then I place another bar after d3 stars. So 0 stars. I place another bar over here. And then I place another bar after d4 star, which is over here. Correct? So it's similar to what you had proposed, but a little bit different. So I'm going from the left. After d1 stars, I place a bar. And then from that point on, after d2 stars, I place another bar. From that point on, after d4 stars, I place another bar, and so on. Right? So di minus 1 is the number of stars between the ith and the I minus 1th bar. Okay. So every configuration of stars and bars gives me an integer tuple. Correct? So for example, if I take okay, so I have 6 stars. I place my goal is 4 bars, 6 stars and 4 bars. Okay, what integer tuple does this correspond to? 2, 0, 2, 1, 3 zeros. Sorry, what is the number of bars? 5. Okay. So 0, 2, 1, 0, 0. Okay. And all of these are integers and the sum is less than or equal to 6. Okay. So every configuration of stars and bars with r stars and m bars gives me a solution to this particular problem. Similarly, every solution to this problem gives me a configuration of stars and bars. Okay. Fine. Okay, so now for the first bar, how many locations do I have? Yeah, r plus 1, right? So I have r plus 1 choices for the first bar. Now what about the second bar? So r plus 1 minus d1. Okay? So now this in some sense reduces to another stars and bars problem with a reduced number of stars. Or what is another way to think about it? Another way to think about it is that I need to pick or choose locations for R bars, sorry, M bars, correct? But some of these can repeat, right? So for example, two bars can have the same location. What is that equal to? Okay, well, let's try to zoom out and then look at the problem as a whole. I can pick R plus 1 locations for all of the M different choices, or all of the M different bars. How many total choices do I have? How many total configurations do I have? Is it R plus 1 choose M? Because R plus 1 choose M would be the case where no two bars can take the same slot. R plus 1 whole power M. Okay. Okay, are you sure that all of them can, all R plus 1 power M configurations are possible? Or are you overcounting something? Uh, so R plus 1 power M, so for example, so you're saying it is R plus 1 to the power M. Right? So the first bar you're going to put, so remember, these bars are not labeled in any way, correct? So right, so suppose for the first bar I place it over here, the second bar I place it over here, the third, fourth and fifth I place over here, correct? So this is the first bar, this is the second bar, third, fourth, fifth, correct? Now another configuration is I place the first bar over here, the second bar over here, the third, fourth and fifth bar over here. But these two are the same configurations, right? So I'm counting it multiple times if I take R plus 1 whole power M. Do you agree? My claim is that this is equal to R plus M choose M, which is also equal to R plus M choose R. So correct. Yes. Yes. Exactly. So of course you have to choose M different things. But what are you basically choosing it out of? Can you pick up a bit? Correct. So, so this basically counts the number of ways of choosing m out of r plus m objects. Right? So in this case, m are the m different bars. So what is r plus m? Why is it exactly equal to r plus? It's not r plus 1, it's not r plus 2, it is r plus m. Correct? Correct? Yes. So can you rephrase that a little bit? You have r plus m, yeah. So you have r plus m empty slots, correct? Okay. Bars, correct. So you put, correct. So you pick locations for the bars. Everything in between is going to be a star. Correct? And the number of ways of picking these is exactly r plus m choose m or r plus m choose r. You can either pick the locations of the bars first or you can pick the locations of the stars first. So it's exactly equal to r plus m choose r, which is what we want. So the dimension of the Reed-Muller code is equal to r plus m choose r. But remember, this is only under the assumption that r is strictly less than q. And this is important because these monomials can take any value up to r, right? If not, then you would have to impose an additional constraint that each each variable cannot have degree more than q minus 1. Since r is less than q, r is less than or equal to q minus 1. So each monomial can go all the way up to r. The degree of each variable can go all the way up to r. Okay, so this gives us the dimension. Now, what about the minimum distance? So once again, we're assuming that r is less than q. Okay, so well, the minimum distance is equal to the minimum Hamming weight. In this case, what are we doing? We're evaluating the polynomial. So a code word is obtained by evaluating a certain polynomial at all possible points. Correct? So in other words, the number of zeros or the Hamming weight of any particular code word. Let's take one particular code word. So this code word is obtained by evaluating the polynomial at q to the m different points. Correct? So what is the Hamming weight equal to? It is basically the number of points over which this polynomial is not equal to 0. Correct? Or in other words, it is q to the m minus the number of roots of this particular polynomial. correct? So we want to know, if we pick any arbitrary polynomial, how many roots can it have? Okay. Now, if it's a degree, so if it's a single variable polynomial, then we know how many roots it can have. How many roots can it have? What's the maximum number of roots it can have? It's a degree R polynomial. It has degree at most R. So the maximum number of roots can be R. It could be strictly less than R, right? But it can't have more than R roots. So if M is equal to 1, then Hamming weight of C is greater than or equal to Q to the M minus R. So it's Q minus R. Correct? We want to generalize this for larger n. And here's the claim. Q to the power M is always greater than or equal to R divided by Q. So the minimum distance is going to be Q to the power M minus R by Q times Q to the power M. Sorry, the number of roots is at most R by Q. So the minimum Hamming distance, or the minimum Hamming weight of the code, is going to be greater than or equal to Q to the power M into 1 minus R by Q, which is Q to the power M minus R times Q to the power M minus 1. It's a bound, right? So how do we prove this? One way of showing this, or one way of interpreting this particular statement, because one is count the number of roots. The other way is the following. Suppose I pick a point at random. Okay? I pick one of the Q to the M points at random, and I evaluate the polynomial at this particular random point. What is the probability that it is equal to 0? Okay? That is going to be exactly equal to number of roots divided by Q to the power this fraction. So I have to pick it uniformly at random. One of the Q to the M points uniformly at random. So we already know that for M equal to 1, it's a polynomial in one variable. We have number of roots divided by, no matter what polynomial it is, right? As long as it has degree at most R, the number of roots divided by Q to the power M is less than or equal to R by Q. Okay, so I want to generalize this to higher M. So let's try an induction step. Suppose that this is true for all polynomials in M minus 1 variables. Okay. Okay, suppose it's true for all m minus 1 variate polynomials. Now I'm given another polynomial in m variables. Right? I want to show that this statement holds for polynomials in m variables. Now I can write any polynomial in m variables in the following way: f0 of x1 to m minus 1 xm power 0 plus f1 1 up to m minus 1 m power 1 so on all the way up to f, let's say t, x1 to xm minus 1 xm power t, right, where t is less than or equal to r, right, where each of these are polynomials in m minus 1 variables, and the degree of each of these cannot be too large. In particular, the degree of fi has to be less than or equal to r minus I, because the total degree should be at most r. So the degree of each of these terms can be at most r. I already have an xm power I over here, so the degree of fi should be at most r minus I. Okay. Any questions? Okay. So now suppose I pick an x1 through xm uniformly at random. Okay. So I want to know what is the probability that f of x1 through xm is equal to 0. Now this, I'll decompose this into two events. So E1 is defined as the event that f t of x1 up to xm is equal to 0. And E2 is the event that xm power t is equal to 0. Given that f t of xm minus 1 x1 up to xm minus 1 is not equal to 0. Okay. Now, if this happens, then certainly either this should happen or this should happen. But just because one of these two happens or both happen, it doesn't mean that this is true, right? We don't, for the moment, we're not even caring about the lower terms, right? So none of these depend on f0, f1, or ft minus 1. I'm only looking at the teeth term over here, right? So the probability of f of x1 to xm equal to 0 is less than or equal to the probability of E1 plus the probability of E2. Do you agree? Why? Yes, but is E1 union E2 equal to this particular event? It is not. Then this is contained in the event E1 union E2. Right? If one of these, so for this to happen, at least one of these must happen. So it's this containment. I mean, it's a strict containment. So the probability of this is less than or equal to probability of E1 union E2, and then using the union bound, this is less than or equal to P of E1 plus P of E2. Okay, what is the probability of E1? So this is the probability that ft, some polynomial in x1 up to xm minus 1 is equal to 0. Do we have an upper bound on this? Yeah. Can you? The question is, we want an upper bound on P of E1 and P of E2. What is the probability of E1? Do we have an upper bound on the probability of E1? Yes. So what is the probability that ft of x1, x2 up to xm minus 1 is equal to 0? No. So what can you say about ft of x1, x2 up to xm minus 1? It's an m minus 1 variate polynomial, and it has degree what? Yeah. R minus t. Right? So ft of x1 up to m minus 1 is an m minus 1 variate polynomial of degree less than or equal to r minus t. Right? So the probability that this is equal to 0 just using the induction step, induction hypothesis, is less than or equal to r minus t divided by q. Okay, fine. So E2, I will change this event a little bit. I'll call this f of x1 up to m equal to 0. Okay, I want to know, so conditioned on x1 up to xm minus 1, what can you say about xm? Xm is independent of x1 up to xm minus 1. Correct? Because I'm picking it uniformly at random. Right? And I'm conditioning on the event that ft of x1 up to xm minus 1 is not equal to 0. Correct? Do you agree? Okay. So conditioned on this event, f as a function of xm is basically a polynomial in one variable of degree t. Right? So conditioned on ft of x1 up to xm minus 1 not equal to 0, f of m is a polynomial of degree exactly equal to t. So it's a univariate polynomial. What is the probability that this is equal to 0? T by q. Right? So the probability of the second event is at most t by q. So what is the probability that f is equal to 0? It is less than or equal to r minus t by q plus t by q, which is r by q. So we started off with the hypothesis that the statement is true for all polynomials of degree m minus 1, and we see that this extends to all polynomials of in m minus 1 variables, and we see that this holds for polynomials in m variables. Just apply induction, and this holds for polynomials in any number of variables. Any questions? Okay, so this was for the specific case where r is less than q. Right? Now, what if r is greater than q? For the general case, what do we do? So in this case, we can show the following. So let f be any non-zero polynomial in m variables the degree of each xi is less than or equal to q minus 1. The total degree of the polynomial is less than or equal to r. Okay. And let s and t be integers positive such that s times q minus 1 plus t is equal to r. You pick any two integers which satisfies this particular constraint, right? Then So if I look at the set of all evaluation points, if q to the such that f of a is not equal to 0, basically now I'm counting the number of points over which it is not 0. Right? In the previous case, I was counting the number of points for which the polynomial is equal to 0. Then this is greater than or equal to q minus t times q raised to m minus s minus 1, which is greater than or equal to q raised to m minus r by q. So, for example, if you had r is strictly less than q, then I can take t. So basically, I can take t equal to r and s equal to 0. I plug that in over here. So t equal to r and s equal to 0. I get q minus t into q to the m minus 1. This is exactly what we had in the previous case. If r is less than q, then take s equal to 0, t equal to r. So this basically satisfies this equality. T s equal to 0 and t equal to r. Then the RHS is equal to q minus r times q to the m minus 1, which is q to the m minus r q to the m minus 1. So this is exactly equal to the minimum distance, right? What we had in the previous case. So this theorem is a special case. Sorry, the previous one was a special case of this particular result. But for r greater than q, the previous result was not valid, so we need something better. Okay, so we'll use the same step again, induction. So suppose that so we want to prove using the induction step. So take m equal to 1, the univariate case, right? Let's look at this. Okay, sorry, there's one more constraint. This t should be less than or equal to q minus 2, and this is true. Okay, so now if it's a univariate polynomial, then r should obviously be equal to r should be less than or equal to q minus 1. So if r is less than or equal to q minus 2, you can simply take this one, r equal to r is less than or equal to q minus 2. So in this case, s equal to 0 and t equals r. The number of zeros that this can have is at most r. So therefore, the number of non-zero number of evaluation points for which the polynomial is non-zero is greater than or equal to q minus r. right? Which is exactly what we have over here. So q minus t q minus t times q raised to s equal to 0. So do you agree? So I'm just using the fact that the number of zeros of the polynomial is equal to r. Right? So the number of points for which it is non-zero is q minus r. And I'm just rewriting it using t and s, nothing else. Okay. Again, case 2, the same statement is true. Case 2 is r equals q minus 1, in which case s equal to 1 and t equals 0, because we want times q minus 1 plus t equal to r. And t should be less than or equal to q minus 2. Right? So if I take t equal to 0 and s to be 2, sorry, s to be equal to 1, then I get q minus 1 equal to q minus 1. So one way of interpreting this particular statement, right, I have this s times q minus 1 plus t equal to r, right? So this is as though, so basically you can think of s and t as the quotient and remainder when you divide r by q minus 1. Okay? Right? So once again, the number of points f is not equal to 0 is greater than or equal to q minus r, which is q minus s into q minus 1, s equal to 1, which is, I want to show that, so this is equal to 1, and the right hand side over here, so this is equal to q t q minus, so r is equal to q minus 1, so this is equal to 1, correct? Now if I substitute this in here, so the right hand side is q minus t q minus t times q raised to m minus s minus 1, which is q minus 0 times q raised to 1 minus s minus 1, which is q into q to the power minus 1 is 1. Correct? Okay. So once again, let us, so we are given f of x1 to xn. So right now we proved it for polynomials in one variable, any degree. Correct? So now suppose we have m variables. Okay. Let's suppose that the statement is true for all degree m minus 1 polynomials, but now we want to, sorry, all polynomials in m minus 1 variables, and now we want to show it for polynomials of m variables. So now we can write f of x1 through xm as, again, as we did previously, f0 times xm power 0 plus f1 times xm power 1 and so on, up to fb times xm power b. So we are assuming that the individual degree of xm is b for some b less than or equal to r, and of course b also has to be less than or equal to q minus 1. So it's less than or equal to the minimum of r and q minus 1. Okay, so now again we have two events, right? So let a1 be the event that f of p of x1 up to xm minus 1 is equal to 0. Sorry, let's say it's not equal to 0, and a2 be the event that f of x1 up to xm minus 1 is not equal to 0, given that fb of x1 up to xm minus 1 is not equal to 0. Okay, so these are kind of similar to the complements of the previous event. So this event in the previous case, we were looking at the event that fb is equal to 0. The other event we looked at was f of x equal to 0, given that fb is equal to 0. Right? Now we're looking at slightly different events, kind of the complement, and we're going to use a different bound. So I can write probability f of 1 to xm not equal to 0. This is less than or equal to, is greater than or equal to the probability of event a1 times the probability of event a2. The probability that f of x equal to 0 is greater than or equal to the probability that f of x is not equal to 0, given this times this probability. Correct? So this is in fact equal to probability f of x1 xm not equal to 0, given fb xm not equal to 0 times probability that fb x1 up to x m minus 1 not equal to 0 plus probability f of x1 to xm not equal to 0, given fb of x1 xm minus 1 equal to 0 times probability fb x1 up to equal to 0. correct? Just law of total probability. And therefore, this probability is greater than or equal to just the first term. Okay, but what are those two probabilities? Probability of A1. So this is the probability that f is not equal to 0 given that fb is not equal to 0, right? So given that fb is not equal to 0, if fb is not equal to 0, then if you look at just the variable xm, this is a polynomial in xm of degree b, right? And how many roots does it have? At most b roots. Okay? So this first case is greater than or equal to q minus b divided by q. Given that fb is not equal to 0, f of xm is a polynomial in xm of degree b, and it can have at most b roots. So the fraction of points for which it is non-zero is q minus b by q. Okay, now what about probability of A2? Again, we can use the induction step, correct? But now the parameters are a little bit confusing. So clearly, this is greater than or equal to, we just use the induction step. So this is greater than or equal to some q minus t prime times q raised to m minus s prime minus 1. Okay? Because I don't know what is the degree of exact degree of fb. This is q minus t prime times q raised to m minus s prime minus 1 I'm just using the induction step over here, correct? Where what are t prime and s prime? Note that fb m minus 1 has total degree less than or equal to m minus b, sorry, r minus b. Correct? So you basically replace r by r minus b over here. So essentially we want s prime times q minus 1 plus t prime equal to r minus b. Okay. So therefore, the probability that f of x1 up to xm is not equal to 0 is greater than or equal to this times this. Okay, so q minus b by q times q minus t prime times q minus m, q raised to m minus s prime minus 1. Okay. Now there are some more steps which I'm not going to formally prove. It doesn't use any deep ideas. It just is a matter of sort of simplifying this under these particular constraints. So you can show that this is greater than or equal to q minus t whole raised to q minus t times q raised to m minus s. Okay. So you can see essentials of coding theory. It's again, so the main idea was just to use induction and use this probabilistic approach. Even though we didn't really have anything random, we sort of, it's a counting problem, but then we're counting the fraction of certain things happening, and that can be expressed as a random event if we take things, if we pick points uniformly at random. And we can show that this is true. Right? So this gives the minimum distance in for the general case. Right? For any general Reed-Muller code, this the number of points for which it is non-zero is greater than or equal to. Okay? So let's stop here. I think it's time for the next class. Any questions?